Right. Now let's see in chemical bonding, chemical bonding, what all basics we need to learn. So let's start with the first one. A bond formation is about a strong attraction between two atoms or two species. Imagine two atoms are separated at a very far distance from each other. So, whatever the amount of nuclear charge, sorry, the electron charge on the surface, and whatever the electron charge on this surface, if they are far away, the repulsions will be weaker. So, you will not see any kind of repulsions. Even between their two protons or proton and electron attraction, it will be hardly observed as long as these two particles are quite far away from each other. So if I plot a separation distance, this distance that is r, okay, and as the separation distance decreases, right? So now what would happen? There would be a certain interaction that will start happening between the atoms. Due to that interactions, there would be either an uh, attraction or repulsion. Got it? Now it all depends upon if it is undergoing attraction, then the potential energy will decrease. If it is undergoing repulsion, then the potential energy will increase. But if there is a repulsion, naturally you will see again the particles will repel each other and the distance between them increases. So, which means whenever there is a repulsion, you will hardly see any change in the potential energy. But if they are getting it attracted, so as they get attracted, the distance between them further decreases and it will keep coming to the point where they almost overlap with each other. Correct? A point where there is the overlap of the orbitals or electron clouds, right? When the overlap of electron clouds happen, that's when we have the maximum amount of potential energy developed. Now usually potential energy is subject to attraction of positive and negative charges, and by uh, we have learned the definition of potential energy earlier in structure of atom. That is how much is the force of attraction, right, multiplied force of attraction multiplied by the distance factor between them. So an attraction between the two charged particles is called as coulombic force, which I can write it as q into q plus, I mean k into q plus into q minus divided by r square, and the distance is r. And now I'll tell you this: positive charge nucleus multiplied by the negative charge electron. That is the product you are supposed to look into. So now positive into negative charge overall will always give you negative value. So this will become K into electron charge, sorry, Z into E, which is the charge of one nucleus, multiplied by electron charge divided by R. So this will be the potential of one nucleus, okay? This is the potential energy of one species. Let's say this is the potential energy of this particular species, this one. Similarly, you will have potential energy for the other species. So adding both of them will get the total potential energy. But mind you, the total potential energy will still remain negative. Okay. So that's what I'm trying to plot here. So usually, whenever there is a chemical bonding happening, the potential energy between them will start increasing in a negative value and it reaches to a minimum value here. And thereafter, further, if you start trying to push the species closer to each other, in that case, the repulsions will be dominate and potential energy drastically increase in the positive scale. So this is a typical curve which you will observe for potential energy, everybody. Yeah. So this would be the potential energy versus the separation distance, everybody. Okay. So keep that in mind whenever there is a potential energy Observed. So uh, this is how the graph is to be assessed for chemical bonding. Now, like I said, the attractive forces holding the atom ions is what we call it as the chemical bonding. Now, what are all the attractions that are observed, everybody? Look into this. This is species 1 and this is species 2, or an atom 1 or an atom 2. So I can say that these electrons present on the outermost shell versus the attraction of nucleus 2, and this electrons present in the outermost shell versus the attraction of nucleus 1. These two would be the ones which are attracting. Of course, these two nucleus will also have repulsion. These two electron densities will also have repulsion. So there are two level of repulsions and two level of attractions. We say a chemical bond is formed when the attractive forces overpower the repulsion forces. So when attractive forces dominate over the repulsive forces, we say the bond has been formed. Okay. So I suppose you got an idea about what is chemical bonding, everybody. Okay. Check. A chemical bonding leads to more stability of the atom. Hence, any bond formation will release the energy. Okay. So the overall energy is released because if you may notice that potential energy is negative. Negative means what? A released energy out of the molecule. Got it? Second, according to according to Kozel and Lewis theory, atoms will acquire octet configuration. Atoms will acquire octet configuration in their valence shells, and that is what we call it as octet rule, which means by means of this attraction, when they form a chemical bonding, and intrinsically, if you notice what is happening here is both the atoms somehow trying to come to a compromise where both of them can have 8 electrons each on the outermost surface. Okay, so that is what Cosell and Lewis theory suggest. Okay, and this type of achievement of 8 electron system is what we call it as octet rule. To practice, I mean, to theoretically show how the you know octet is actually forming, you have to go through Lewis structures or Lewis dot structures. So Lewis dot structures suggest that how many number of electrons in the valence shell every atom would have. For instance, if I take hydrogen, it will have only one electron in the valence shell, while helium will have two electrons in the valence shell, and lithium will again have only one electron in the valence shell. Beryllium will have two electrons. Boron would have three electrons. Carbon would have four electrons. And nitrogen would have five electrons. Now, what I'll do to showcase the five electron, this time I'll show it with a pair on one end. And similarly for oxygen, it will be two pairs and like two unpaired electrons. Fluorine, which is three pairs and one unpaired electrons here. Okay, which pretty much matches with their outermost configuration also. This is 1s1 and 1s2. 1s2. This is 2s1, 2s2. This is 2p1, 2p2, 2p3, 2p4, and 2p5. And by the time it comes to neon, all of them would be appearing like octet. So have you noticed that from here till fluorine, they have no complete octet, which means 8 electron system is not observed. So their whole objective is to somehow get those 8 electrons. That's the reason that why they are trying to dominate their attractive forces compared to the repulsive forces. Okay. Now, the first three becomes very, very difficult to get the octet. So these are the exceptions. The hydrogen, helium, and lithium. They would not be getting the octet easily. That's why they will be satisfied or they'll be happy getting a duplet. That means only two electron system. So they would always like to form a two electron system. For example, I have a hydrogen with single electron. I have another hydrogen with single electron. These two hydrogens, as they come close to each other to make a bond, they will come to a compromise that we both will share the electrons with each other this way. And this sharing is being shown like this. So the suppose if this is the electron density of the hydrogen on the left, and this is the electron density of hydrogen on the right. So now you can see there is a shared region between them. This is a shared region, correct? So the shared region is typically like this. Sorry, the shared region is typically like this. This is how the shared region is. Got it? So due to that shared region, so this is completing duplet form, and this is also completing duplet form. So if there is one pair, that means two electrons is one pair. If one pair is shared, when we make a bond, this is way we represent. This is called bond line structure. Bond line structure. That is, we are trying to show how many bonds are forming. Got it? If there is only one bond between the two atoms, we refer that as single bond. So there is a single bond between hydrogen and hydrogen, and that is enough for both of them to achieve duplet form. Okay. And remember, bond line is written only for covalent bonds. Only for covalent bonds. Now, what are covalent bonds? I'll give you a better description going ahead. So just as of now, keep that in mind. What if I have something like a lithium, which is also having a single electron on it, and then I have something like fluorine, which has 7 electrons on it. In this case, what would happen? Lithium would actually lose out its electrons completely. Lithium will completely lose out its electron, while fluorine would acquire one extra electron to complete its octet. This would be fluorine. Now, mind you, I'm not showing some kind of an overlap anymore. I'm not showing some kind of an overlap. I'm just trying to make sure that they are close, but there is no overlap as such. Okay. Because lithium has completely lost the electron, it acquires positive charge. Fluorine acquires negative charge. In such cases, when there is a complete charge on the species, on both of them, then I would represent the bond like this, La plus and F minus. And notice, mind you, there is no line I'm drawing between them. In such case, without any line, if you're just representing two ions in the bracket like this, then we refer this as ionic bond, which is trying to mention that there is only an attraction between the atoms, but there is no precise bond which is forming in between them. We say there is a bond forming, but this bond is an ionic bond. So we will not be pushing any lines like this. Okay, correct. Now, what is the purpose of lithium to lose out one electron? Because lithium originally had one s2 and two s1. And now, since it has lost that electron, it has again achieved 1s2. So this has now become 1s2 here. This lithium's configuration is 1s2, while fluorine's configuration is 2s2 and 2p6, right? So which clearly suggests that it has 6 plus 2 plus 6, 8 electrons, and lithium has 2 electrons now. So both of them, lithium is satisfying its duplet, fluorine is satisfying its octet. This is a kind of compromise that comes between the atoms which creates the bonds. Clear? Now, there are mainly three types of interactions that we will be mainly discussing. First one is covalent bond. where there is a sharing of electrons so that both can review the same electrons and try to complete their octet. Second is a ionic bond where there is a complete transfer of electron from one species to the other species. Third one is a coordinate covalent bond. Here it is a sharing of electron, but only by one species is shared. The other species is not sharing, only one species is sharing the electrons. Then we call it as coordinate covalent bond. For example, if you have, you know, sorry, ammonia. Ammonia has three bonds and one pair which is non-bonded. This, when you bring towards BF3, BF and 3. Here also it has three bonds. Okay. But you know that as per octet rule, every central atom must have 8 electrons on it. Now, every single line of bond represents 2 electrons. So we have 2 electrons here, 2 electrons here, 2 electrons here, and 2 electrons here. So total 8. So this nitrogen has fulfilled its octet. While in the case of boron and fluorine, there are 2 electrons here, 2 here, and 2 here, only 6. Which means I can show it like an empty box here, where the lone pair, I mean this non-bonded electrons will be ready to be shared by boron. On sharing, so what do we get here? Nitrogen and boron both will share, because now nitrogen is sharing. It's like nitrogen losing out its electrons, so it would acquire a positive charge. And boron is like gaining one extra electron into its system, that makes it negative charge. So this kind of a connection between positive negative charges, this is what we call it as coordinate covalent bond. Okay. So it is a covalent bond, but it is due to our lone pair being donating on it. All good. Now, whenever we want to make a covalent bond, we'll have learned in periodic properties that the electron negative difference between the two atoms must be less than 1.7. If it is less than 1.7, typically we expect them to form only covalent bonds. Okay. Ionic bonds are less likely to happen. So the same thing happens here between H and O, H and F, H and Cl, H and Br, H and I, C and H, H and S, H and P, H and Sc. All of these would form covalent bonds. Okay. Let me show you one by one how the O2 molecule is formed. Right? How the O2 molecule is formed. So check it out. First, write the Lewis dot structure. That is, it has 6 electrons in the valence shell, and we know that this is how we write it now. And I have to write the same thing for second molecule also. And imagine both of these are interacting with each other. Now, what kind of a compromise they will make? That this oxygen and this oxygen realizes that if only they both can share together and not one electron, two electrons each, that's when the octet would be completed. That is, this oxygen with lone pair, I mean, sorry, bond, both of them are sharing one electron here, this way. And now, rest of the electrons, if we compare, we have here this way, and we have here this way. This is the rest of the electrons. From the first oxygen's point of view, if you notice, this is, sorry, this is completing octet. Check out. So now the oxygen get a feeling that it has 8 electrons in the valence shell. You can see 4 dots here and 4 dots here. While on the other hand, even this oxygen would get a feeling that my octet is completed. Right? So you can see those 4 electrons in between are shared by both the oxygens. And every 2 electrons is one pair. So therefore we say this as 2 bonded pair of electrons. So 2 bonded pair of electrons. And now notice this one, two, three, four. They are not participating in the bond, but they are there to just complete the octet. So these are called non-bonded electrons. These are non-bonded electron pairs. So these non-bonded electron pairs is what we call it as lone pairs. This is what we call it as lone pairs. So therefore, if I write the oxygen-oxygen bond, I would write it like this: O, double bond O, lone pair and lone pair, lone pair and lone pair. So it appears like octet is completed. So this is the Lewis dot structure. Lewis structure. And this Lewis structure has how many lone pairs and bond pairs? It will have two bond pairs and four lone pairs. Everybody clear how the O2 works here? This is how you represent the bond, everyone. Okay. See the next one. In case if you have N2, N has 5 electrons like this, plus another N, 5 electrons. And to get itself into octet completion, the best possible scenario is to make all three electrons shared with each other and one lone pair or a non-bonded electrons on each side. This way, again, you notice this part here. This nitrogen would say, I have completed my octet. Okay, which is fair. And similarly, this nitrogen would say, I have also completed my octet. Right? So you can clearly see that the region between them is shared. Okay. So therefore, how do we write the bonding here? N triple bond N with lone pair and lone pair. So three bonds are there. That's why I'm using the word triple bond. And how many bond pairs and lone pairs we have? You can see number of bond pairs here are 3. Number of lone pairs here are 2. Got it? See the case for HF now. In the case of HF, we have H with a single electron, fluorine with 7 electrons. So fluorine would want to get an octet completed and hydrogen want to get a duplet completed. So that's the compromise they'll come across. Only one bond with fluorine already having 6 electrons. Now, as per hydrogen, it has completed its duplet form. It has completed its duplet form, correct? And as per fluorine, it would say, I have completed my octet form. So you can see fluorine has completed the octet form. So we can write this as H with single line F. That is how you represent in uh, Lewis dot structure. So now number of bond pairs, how many we have? 1. Number of lone pairs we have is 3. Okay. Please go through it. If you have any doubt, you can ask me again. Please check. To the next point. Between the two atoms, we can never go beyond 3 bonds. Okay. So between two atoms, we can have a single bond, double bond, or a triple bond. You cannot have quadruple bond, right? So 4 bonds at a time are not possible because every element would have at least 4, I would say, if they have at least 4 electrons, for in the case of carbon, we might expect that, sir, why don't we share all 4 electrons from one end and all 4 electrons from the other end? That kind of possibility, theoretically can be made, but practically it is not possible. Okay. Now, while writing the Lewis structures, guys, what are all the basic rules that you need to follow? First, identify what is a central atom. Generally, the one which is less electronegative element and ready to share bonds with multiple atoms. Ready to share electrons with multiple atoms, that would become central atom. Second, locate the side atoms uniformly. That means you have to start identifying the side atoms which are connected to it and keep them as uniform as possible. Find the total number of valence electrons present in it. Okay, so that is how many valence electrons does it have. We can figure it out and then distribute the valence electrons to ensure all of them get octet completed or duplet completed. Now I have to distribute all those electrons again, right? Count all of the valence electrons, keep it in your hand, and again distribute between those two atoms. And you distribute such a way that all the atoms present in them should either get a duplet form, and in case if it is hydrogen, helium, or lithium, it should get a duplet form. Okay. Let me show you with the example of ammonia. Okay. If I were to figure out, what is the structure of ammonia or what is the number of bonds present in NH3. Okay. So first thing I will do is check out what are the electrons present on nitrogen. So there are supposed to be 5 electrons. This is nitrogen. And then we have 3 moles of H dot. Okay. So now the nitrogen realizes that if at all I make the bonding with one hydrogen here, and one hydrogen here, I'll be able to complete the octet. And that's what it will do. So we'll have N double bond, I mean lone pair, lone pair, lone pair, and lone pair here. So here I can make it into bonded pair this way. Okay. Now complete the octet of nitrogen. Yes, the octet of nitrogen is completed. And at the same time, the duplet of hydrogen here, here is completed. The duplet of all 3 hydrogens is also completed. So if I write in a bond line structure, it will be like nitrogen having H, and H with a lone pair on it. This is the way you represent the Lewis structures. So if I figure out number of bond pairs and number of lone pairs, bond pairs you will see there are 3, lone pairs you will see there is 1. Okay, so this is the structure of NH3. Got it? So have you noticed something? What did I do here? So I represented, first I identified number of atoms present and I mean, which one should be at the center, because I know that nitrogen can only take multiple bonds. Hydrogen can't take multiple bonds. So I made nitrogen at the center. Then I surrounded the hydrogens uniformly. Uniformity is like, 4 different directions: north, south, east, west. That's the uniform way of distribution. So I got 3 nitrogens distributed. And on that hydrogens, you'll see how many electrons are required. So 2 electrons are required, and that's what we have done. Got it? See, another way is to calculate something which is valence electrons of nitrogen. Valence electrons of nitrogen is 5. Valence electrons, of nitrogen is 5. And if it comes to number of electrons required to complete the octet, okay, electrons required to complete the octet. Complete the octet, which you call it as factor R. R is 8. V is 5. R is 8. Okay. And now I can say R minus V. Okay. So we can call this as R here minus V. How many we have? 3. Correct. So which means these 3 should be the bonded electrons. These 3 should be bonded electrons. Okay. And so I'll call the bonded electrons. I call the bonded electrons as B. Okay. And the remaining unshared electrons will always be equal to V minus B, which is 5 minus 3. So how many we have? 2. So that becomes the unshared electron. So you can see here also it is all mapping up here. So required is 8. Out of that we have 5. So that means 3 should be somewhere shared. So that is those 3. And out of the 5, if I remove the 3 shared ones, how much is left? 2. So that will be lone pair present. Correct? That is what exactly I'm trying to put that as a rule here. Okay. Let's do the same thing for CO2 here. CO2, carbon has 4 electrons. Oxygen, 2 of the oxygens will have 6 electrons like this. And only way to get a complete octet is carbon share 2 electrons on one end and 2 electrons on the other end. While oxygen share 2 electrons on one end and another oxygen share 2 electrons on the other end. Like this. So now you notice the number of electrons of oxygen. 8 octet is completed. Okay. Here also octet is completed. Okay. And if you notice this one, here also carbons octet is completed. Check. Here also carbons octet is completed. So if I write this in the bond line structure, I would get this as O, double bond C, double bond O, and then we have lone pair and lone pair here, lone pair and lone pair here. Okay. This is a Lewis structure where I can represent the octet completion for both of them. Now notice, because now oxygen is also sufficiently involving in the bond, what we can do, we can actually first write the total number of electrons of both of them. So valence electrons total will be equal to 4 plus 6 plus 6. Got it? So how many we have? 16 valence electrons. So R is an ideal number of electrons required for each atom to get octet, which is 8 plus 8 plus 8. Okay. So which is 18. Sorry, 24. Okay. This is the ideal number of electrons required to complete the octet. So the difference of this R minus V will give us B electrons, that is bonded electrons. So which is 24 minus 16 will make it 8 bonded electrons. Okay, 8 bonded electrons. And I told you this also, number of lone pair electrons, how many electrons must be in lone pairs, will be total valence electrons minus how many bonded electrons we have. Bonded electrons. So therefore, 16 minus 8, which makes it 8 electrons. 8 bonded electrons. So can I write this? 8 bonded electron means 4 lone pairs. Okay. And 8 lone pair electrons means 4 lone pairs. And 8 bonded electron means 4 bonded pairs. So even by, see, suppose if you didn't know that, okay, imagine you didn't know this, you didn't know how to, sir, make the, correct structure. No worries, just use this basic maths. So basic maths is find out the total number of valence electrons, ideally how much it is required, identify what is the bonded electrons present here, you will get to know how many lone pair electrons present here, you get to know. Now you redistribute everything. So that is, I have carbon and oxygen. This is called skeleton. Okay. I was sent carbon at the center because it is less electronegative as per Lewis rules. And then I need to have 8 bonded electrons. So the best possible scenario is that 1, 2, 3, 4. So 4 pairs I'll place it this way. And now I have 4 lone pairs. 4 lone pairs I will place like this. 1 lone pair here, 2 lone pair here, 3 lone pair here, and 4 lone pair here. So observe this carefully here. The octet of this oxygen is completed. Octet of this oxygen is completed. And then octet of this carbon is also completed. Correct? So octet of this carbon is also completed, which is exactly what we got. Okay. So hence we'll get this as O, double bond C, double bond O. Put this lone pairs appropriately. So this will become Lewis structure. This will become Lewis structure. Okay. Okay. Also known as bond line structure. So number of bond pairs, everybody, or four. Number of lone pairs, four. This is a final go. All good? You guys listen up. Now imagine if you are able to get, maximum number of bonds. Sorry, if you are able to write multiple Lewis structures, correct? The first rule is what, everybody? That try to emphasize that everybody gets the octet completed. While doing so, you also need to make sure that there are minimum charges that you are getting on the atom and there are maximum bonds that you can pull out of them. Only those type of structures are accepted. Got it? So if at all I have to complete the octet of CH, I mean for carbon for instance, I need to search for that particular route where I have maximum bonds completed or maximum number of bonds observed. So for example, if you have CH4, carbon which is supposed to have 4 electrons plus 4 hydrogen atoms, that would give us carbon with 8 electrons surrounding it and 4 hydrogens surrounding it. Okay. So now you can notice the octet is completed for this carbon and duplet is completed for these hydrogens. So both are happy here. So you'll write the bond line structure as C and H, H, H and H. So number of bonded pairs in this case are 4. There are no lone pairs present on it. Okay. So this is the bond line structure, right? So this is the bond line structure. These are number of bonds and lone pairs and also Lewis structure. All good? Right. Now, think in the same lines and I want you to do NO2 plus O3 and P4. Please try these four. Try these three quickly. Okay. Try to write the Lewis structure. First, figure out how many valence electrons are there. Check out how many bond pairs you can put some probability and see which all bonds will be better. Correct. And try to figure out the structure. First case, NO2 plus, nitrogen is less electronegative. So I know that nitrogen has total of 5 electrons. Okay, just a second. Nitrogen we have that plus 2 moles of oxygen here. You know that we have dot and dot here. And now notice something. I have to actually release out one electron also. I have to remove out one electron as well. So in that case, what are the valence electrons, everybody? So you can see this is 5 plus 6 plus 6 minus 1. Got it? So that makes it 16. Ideally, how much amount of electrons are required? 8 plus 8 plus 8. So total 24 required. So R minus V is 8, which means 4 bonded pairs. And okay, V minus B bonded pairs will be 16 minus 8, which is 8 electrons or 4 lone pairs. So this is exactly like carbon dioxide, guys. The way we worked out for carbon dioxide, it is the same thing. So that means N, we have 2 bonds here and 2 sharings here. Then we have oxygen with 4 electrons here. Okay. Okay. So this is the one, and this is the bond we have. And next, here we have 8 electrons. Here, this is the bond formation. So therefore, we have O, double bond N, double bond O. Lone pair, lone pair, lone pair, and lone pair. That's it. Okay. So this is the final bond formation. Clear? So we can see how many bond pairs we have. Bond pairs we have are 4. Lone pairs we have are 4. Got it? In the case of O3, I'm directly writing, guys. You can do the working later. So we have 3 moles of oxygen here as they combine with each other. So I would get like this: O double bond, uh, bonded electrons here and one bonded electron here. Acha, listen, I forgot to mention that plus charge here. Sorry. So here, total we had one plus charge here. So you can write it like this way with plus charge. Okay. So then we have O, and then we have 3 lone pairs here and 2 lone pairs here. Sorry. Yeah, 2 lone pairs here. Now check out the octet completion. This oxygen is completed is octet. This oxygen has also completed is octet. And the central one has also completed its octet. But it should be with one lone pair on it. Yeah. So one lone pair on it. So now the octet is complete. So if I write the bond line structure, it is like O, double bond O, single bond O. Here there is a lone pair. Here there are 2 lone pairs. Here there are 3 lone pairs in fact. This is how the structure is. Okay. So you can see number of bonded pairs. Bonded pairs are 3. 3 bonded pairs. Number of lone pairs here 3 plus 3, 6. 6 lone pairs present now. Okay. Lastly, check out P4. There are 4 phosphorus atoms which has electrons like this. So what if all phosphorus are connected to each other with at least one bond? So that's how we can get P one pair, sharing of one pair of electron with another P, here also with another P, and here also with another P. Correct? So similarly, here also we have one sharing, here also we have one sharing. Correct? And between these two also there is one sharing. These are all shared electrons. Got it? So let me show you. Between these two there is one sharing of electrons. Between these two there is one sharing of electrons. Okay? Let me just delete this part. These two. Now, between these two there is one sharing of electrons like this. One pair of sharing of electrons. And now, between these two there is one sharing of electron. One pair of sharing. Between these two there is one pair of sharing. Correct? And it appears like, this has shared 3. This has shared 3. But the middle, these two has not shared anything. So for that, I'm writing something extra from here. Okay. Between these two, there is one sharing of electrons like this, because I can't show it in the same structure here. So I'm showing it like this. So in the bond line form, if at all I write it, it is like P P, P, and P. Here there is one bond, 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 and bond. Between these two, there is a bond, and between these two, there is a bond, like this. This is how the bonds are. And each of them, to complete the octet, must have their respective lone pair on it. So here, like this, like this, like this, and like this. These are their respective lone pairs. So count each of them is completing the octet. Hence, the number of bond pairs in this case is 1, 2, 3, 4. So you can count these lines 1, 2, 3, 4, 5, 6. So total we have 6 lines. So bond pairs are 6, lone pairs are 4. Okay. So P4 is difficult to visualize unless you have more clarity on the number of bonds. It will be difficult to visualize. So I think you guys can check it out and learn from here. Okay. Any doubt here?